Different concepts regarding current electricity 1. In the diagram, we can consider two resistors which are connected in parallel combination. These are the two resistors of resistances R1 and R2 which are connected in parallel combination. I is the main current which is flowing through this parallel combination of resistances. Current flowing through R1 is I1 and current flowing through the other resistance R2 is I2. V is a potential difference across the resistance R1 and R2. In this case, potential difference across the resistors R1 and R2 are same, that is V. Current flowing through the resistance R1 is I1, which is R2 divided by R1 plus R2 into I. I1 is equal R2 divided by R1 plus R2 into I. That is the current flowing through the resistance R1. Similarly, current flowing through the other resistance R2 is I2, which is R1 divided by R1 plus R2 into I. R1 divided by R1 plus R2 into I. That is what the current flowing through the resistance R2. Potential difference across the resistance R1 or R2 is V, which is I1 R1 equal R2, I2 R2 equal main current I into RP, where RP is the equivalent resistance of this parallel combination, which is equal to R1 R2 divided by R1 plus R2. So, in the diagram, current flowing through the resistance R1 is I1, current flowing through the resistance R1 is I1, and this current expression of this current I1 is R2 divided by R1 plus R2 bracket closed into main current I. That means I1 is equal to R2 divided by R1 plus R2 into I. Similarly, current flowing through the resistor R2 is I2, which is R1 divided by R1 plus R2 into I. Now, the next case we have to consider the next formula, next case. Here we can consider that three resistors are connected in parallel combination. Three resistors of resistances R1, R2, R3 are connected in parallel combination between the 2 points A and B. R1, R2 and R3 are the resistances of these three resistors. I is the main current. Current flowing through R1 is I1, current flowing through R2 is I2, and current flowing through the third resistance R3 is I3. Now I1, current flowing through the first resistance R1 is I1, which is R2 R3 divided by R1 R2 plus R2 R1 R3 plus R2 R3 into I. That is the current flowing through the first resistance R1. V is the potential difference across the three resistors R1, R2 and R3. V is the potential difference across all the resistances R1, R2, R3 which are connected in parallel combination, and this potential difference V is I1 R1 equal I2 R2 equal I3 R3 equal main current I into RP, where equivalent resistance of this parallel combination RP is R1 R2 R3 divided by R1 R2 plus R1 R3 plus R2 R3. That is the equivalent resistance of the parallel combination of three resistors. Similarly, current flowing through the resistor R2 is I2, which is what divided by something divided by R1 R2 plus R1 R3 plus R2 R3. In the numerator, we should have what? In the numerator of the expression I2, there should be R1 into R3, and I3 is equal what into I? It should be R1 R2 divided by R1 R2 plus R1 R3 plus R2 R3 bracket close into main current I. So I3 is the current. I3 is the current flowing through the third resistor of resistance R3, and I3 is equal to R1 R2 divided by R1 R2 plus R1 R3 plus R2 R3 into main current I. That is the current flowing through the third resistor of resistance R3. Now we can consider the third case or third formula, that is an electric cell of EMF E an internal resistance R is connected to an external resistance capital R and current is generated from positive plate of the battery or cell, and current I is flowing through the external resistance R from left to right. I is the current flowing through the circuit, and similarly current flows from negative plate to the positive plate of the cell through the internal resistance R. We know that current is equal to EMF divided by total resistance of the circuit. Current equal EMF divided by total resistance of the circuit. Therefore, I is equal E divided by R plus small r. Capital R is the external resistance, small r is the internal resistance of the cell. I equal E divided by R plus R. That is the expression of current. That is the expression of current flowing through the external resistance. Flowing through the external resistance, capital R. External resistance, capital R. I equal E divided by R plus R. Next concept or next formula in the connection of the chapter current electricity 1. Number 4, again we can consider two electric cells which are connected in series combination, and this series combination of two electric cells are connected to an external resistance capital R. E and E are the EMFs of the two cells, and these two cells have the same internal resistance. I is the current which is flowing through the external resistance R from left to right. Two cells having same EMFs are connected in parallel in series combination here, and current is equal to total EMF by total resistance, that is E plus E divided by R plus R. Therefore, we get I as equal to E divided by R plus small r, capital R plus small r. I is equal to 2E divided by R plus R. Number 5. Now we can consider two electric cells having same EMF or equal EMF are connected in parallel combination. These are the two electric cells which are connected in parallel combination, and this parallel combination of two cells are connected to an external resistance capital R. E and R. E is the EMF of each cell, R is the internal resistance, and capital R is the external resistance, and I is the current which is flowing through the external resistance capital R. In this case, current I is equal to EMF E divided by R plus RT, where so therefore I is equal to what, and in this case RP is the equivalent resistance of two cells connected in parallel combination, and we get I as equal E divided by R plus R by 2. Now again we can consider parallel combination of two cells, Now we consider a parallel combination of two cells having different EMFs E1 and E2. R1 and R2 are the internal resistance of the cells. Capital R is the resistance, external resistance which is connected to the parallel combination. I is the current which is flowing through the external resistance capital R. I1 and I2 are the currents which are generated from the cells of EMFs E1 and E2. Now we have to know the expression of terminal voltage of each cell and current I flowing through the external resistance capital R. And terminal voltage, expression of terminal voltage V is E1 by R1 plus E2 by R2 whole divided by 1 by capital R plus 1 by small r1 plus 1 by small r2. Therefore, I is equal E1 by R1 plus E2 by R2 1 plus capital R bracket opened 1 by R1 plus 1 by R2 plus 1 by R2. That is the expression of current I flowing through the external resistance capital R. V is the terminal voltage of each cell. V is the terminal voltage of the cell of EMF E1, and V is also the potential difference across the external resistance capital R. And in this case, equivalent EMF of the cell will be equivalent EMF of the cell will be E1 R2 plus E1 R1 E2 R1 whole divided by R1 plus R2 whole divided by R1 plus R2. Number 7. Now we can consider series combination of two cells having different EMFs E1 and E2. This is the series combination of two cells, and this series combination of two cells is connected to an external resistance capital R. This is the circuit diagram. E1 and E2 are the EMFs of the two cells which are connected in series combination. R1 and R2 are the internal resistances, and capital R is the external resistance. I is the current which is flowing through the external resistance R and generated from the two cells. We can denote positive plate and negative plate of the cells. In this case, positive plate and negative plates of the cells are denoted. Current I is equal to total EMF is E1 plus E2, where negative plate of the cell E1 is connected to the positive plate of the cell E2. And expression of current I is equal E1 plus E2 divided by total resistance of the circuit will be capital R plus under bracket small r1 plus small r2. That is the expression of current flowing through the external resistance R. I is equal E1 plus E2 divided by R plus R1 plus R2. The next concept is number 8 concept. Two cells are connected in the reverse way. That means the negative plates of the two cells are connected to each other, and positive plates will be connected to each other through an external resistance capital R. In the last case, negative plate of the cell E1 is connected to the positive plate of the cell E2. But here, two cells are connected in series combination in the opposite manner or in the reverse manner. E1, E2 are the EMFs of the two cells, in which negative plate of the cell E1 is connected to the negative plate of the cell E2. That means these two cells are connected in series combination in the reverse manner, and we can consider that E1 is greater than E2. That means EMF of the cell E1 is greater than the EMF of the second cell E2, and E1 dominates. That's why current I is generated from the positive terminal or plate of the cell E1, and current I flows in this way through the circuit. Through the internal resistance R1, current I is flowing from negative plate to positive plate, but through the internal resistance R2, current is flowing from positive plate to negative plate of the cell. That means through the internal resistance R2, current I is flowing in the reverse way or in the opposite manner. Through the internal resistance E2, current I is flowing from positive plate to negative plate, but through the cell of EMF E1, current is flowing from negative plate to positive plate of the cell of EMF E1. In this case, current expression of current I will be E1 minus E2 divided by R plus R1 plus R2, capital R plus small r1 plus small r2. Current I is equal to E1 minus E2 divided by R plus R1 plus R2, where negative plate of the cell E1 is connected to the negative plate of the cell E2. That's why the total EMF will be E1 minus E2. Number 1 concept will be what? This is the circuit diagram. Two cells are connected in the same manner. That means negative terminal of a cell is connected to the positive terminal of the cell, and this series combination of two cells are connected to mixed combination of resistors. This is the mixed combination of resistors. E1 and E2 are the EMFs of the two cells which are connected to the series combination. Capital R1, capital R2 and R3 are the external resistance here. Capital R2 and R3 are connected in parallel combination. A current I is generated from the positive terminal of the cell of EMF E1, and this current I is flowing from left to right through the resistances R1, R2 and R3. I2 and I3 are the currents flowing through the resistors of resistances R2 and R3. We can denote the direction of current, main current I, in this way, and main current I, expression of main current I will be equal. We have to know the expression of main current I2 and I3. Main current I and I2 and I3. I2 is the current flowing through the resistance R2. Expression of main current I is total EMF will be E1 plus E2 divided by R1 plus equivalent resistance of R2 and R3. That should be R2 R3 divided by R2 plus R3 plus sum of all the internal resistance of the cells R1 small R1 plus small R2. What about I2? Current flowing through the resistance R2 will be equal R3 divided by R2 plus R3 into I. I2 is equal to R3 divided by R2 plus R3 into I. Similarly, I3 is equal to R2 divided by R2 plus R3 into whole multiplied by main current I. Number 10 formula, in this case 3 resistors will be connected as shown in the figure. These are the 3 resistors which are connected to each other in this way: R1, R2 and R3. R1, R2, R3 are the resistances which are connected to each other in this way as shown in the figure between the 2 points A and D. And 2 terminals of R1, R2 are connected by a connecting wire as shown in the figure. Similarly, 2 terminals of R2 and R3 will be connected to another connecting wire. Another connecting wire as shown in the figure. Two terminals of R2 and R3 are connected to each other by a connecting wire as shown in the figure. And apparently these 3 resistances R1, R2, R3 are connected in series combination. But here we have to find the equivalent resistance between the 2 points A and D. That means RAD equal question mark. Here we have to find the equivalent resistance between A and D. Potentials at the point AC, B and D are VA, VC, VB and VD. Potential difference across the resistance R1 is V1. Potential difference across the resistance R2 is V2, and V3 is the potential difference across the third resistor of resistance R3. Let V1, V2 and V3 be the V1, V2 and V3 be the potential difference across the resistances R1, R2 and R3. V1, V2 and V3 be the potential difference across the resistors of resistances R1, R2 and R3. Now VA is the potential at the point A. VA is the potential at the point A, which is equal to the potential at the point B. That means VA equal VB as the 2 points A and B are connected by a connecting wire. VA equal VB as the 2 points A and B are connected by a connecting wire, or are connected to each other by a connecting wire or conducting wire. Connecting wire or conducting wire of zero resistance. Conducting wire of zero resistance. Similarly, VC equal VD. VC is equal to VD. Potential at the points C and D will be same or will be equal to each other. Therefore, V1 is equal to VA minus VC. V1 is equal to VA minus VC, that is the potential difference across the resistor of resistance R1. V1 equal VA minus VC, which is the potential difference across the resistance R1. Similarly, V2 is equal to VB minus VC, as VA is greater than VD and VB is greater than VC. V2 is equal to VB minus VC. That is the potential difference across the resistance R2. V2 is equal to VB minus VC. Similarly, V3, that is the potential difference across the resistance R3, will be what? Which one is correct? VB minus VD or VD minus VB? In this case, V3 will be equal to VB minus VD, because the potential at B is greater than potential at D. That means VB is greater than VD. Therefore, V2 is equal to VB minus VC. Writing the expression of V2 again, VB minus VC equal VA minus VD. In this case, the potential difference V2 is equal to VB minus VC, but the potential VB is equal to potential VA. So that's why in place of V2, what we can write, VA minus VD. So V2 is equal to VA minus VD, which is equation 2, and V1 was equal to VA minus VC, which was equation 1. Now V3 is equal to VB minus VD. Therefore, V3 equal to VA minus VD, since VB equal to VA. VB is equal to VA and VC is equal to VD. Therefore, we get V3 as equal VA minus VD, which is equation 3. From equations 1, 2 and 3. From equations 1, 2 and 3, we get V1 is equal to V2 is equal to V3. V1 is equal to V2 is equal to V3. That is, the potential differences across all the three resistors of resistances R1, R2, R3 are same. Hence, we can say that potential difference or PD across the three resistors of resistances R1, R2 and R3. R1, R2 and R3 are same, and these three resistors are connected in parallel between the 2 points A and D. Are connected in parallel combination between the 2 points A and D, and they will appear to be connected in parallel combination, between the 2 points A and D. We can draw the parallel combination of these three resistors of resistances R1, R2 and R3. This is the parallel combination of three resistors R1, R2, R3 between the 2 points A and D. As the potential difference across the three resistors are same, that's why they will appear to be connected in parallel combination. Therefore, Rp equal R1, R2, R3 divided by R1, R2 plus R1, R3 plus R2, R3. That is the equivalent resistance of the parallel combination of three resistors, or equivalent resistance between the 2 points A and D. Rp equal R1, R2, R3 divided by R1, R2 plus R1, R3 plus R2, R3, which is the equivalent resistance between the 2 points A and D. Number 11, in this network or in this circuit, 5 resistors are connected as shown in the figure. Here there will be 5 resistors which will be connected between the 2 points A and C. Number 11, in this circuit, 5 resistors are connected as shown in the figure. 5 resistors of resistances R1, R2, R3, R4 and R5 are connected between the 2 points A and C. Now the resistances R1, R2, R3 and R4 are connected by following Z shape. They are connected by following Z shape. R1, R2 and R3 and R4 are connected as according to Z shape between the 2 points A and C. Fifth resistor of resistance R5 is connected between the 2 points B and D. According to Winston bridge principle, according to Winston bridge principle, if number one VB equal VD, that means potentials at the 2 points B and D are same. If VB equal VD, that is the potentials at the point B and D are same. And here number two, the current flowing through the fifth resistor R5 is I5 is 0. If current flowing through the resistance R5, that is I5 equals 0, in that case the fifth resistor of resistance R5 becomes ineffective. Then R1 by R2 will be equal to R3 by R4. If the ratio of resistances above R5, if the ratio of the middle resistance R5, that is R1 by R2, is equal to the ratio of resistances below R5, that is equal to R3 by R4. If R1 by R2 is equal to R3 by R4, in that case the resistance R5 can be neglected. The middle resistance R5 can be neglected. As R5 becomes ineffective and no current flows through the middle resistance R5, R5 can be neglected or removed from the circuit, and if R5 is removed from the circuit between the 2 points A and C, in that case we shall get this type of circuit. A and C are the 2 points, between them R1, R2, R3 and R4. R3 and R4 are connected and R5 can be neglected. Equivalent circuit diagram of this will be what? There will be two resistances which will be connected in parallel combination between A and C. Here Rs and Rs prime are the equivalent resistances of R1, R2 and R3, R4. Rs is equal to R1 plus R2, which is the equivalent resistance of the series combination of two resistors of resistances R1 and R2. Rs equal R1 plus R2, which is the equivalent resistance of the series combination of R1 and R2. R1 R2 are connected in series combination between the 2 points A and C, and equivalent resistance of them is Rs, which is equal to R1 plus R2. Similarly, Rs prime is equal to R3 plus R4. Rs prime equal R3 plus R4, which is also the equivalent resistance, of the series combination of the two resistors of resistances R3 and R4. Therefore, RAC, equivalent resistance between the 2 points A and C, is Rs dot Rs prime divided by Rs plus Rs prime, because Rs and Rs prime are connected in parallel combination between the 2 points A and C. RAC is equal Rs dot Rs prime divided by Rs plus Rs prime, which is the equivalent resistance between the 2 points A and C. Number 12 concept or formula will be as shown in the figure. In this case, 5 resistors are connected in a triangular shape. 5 resistors are connected in a shape of triangle as shown in the figure. The resistors are R1, R2, R3, R4 and R5. A and B are the two open terminals, and we have to find the equivalent resistance between the 2 points A and B. That is, RAB will be equal to question mark. And if A and B are stretched towards left and right, we get the circuit diagram as shown in the figure. In this case, that 5 resistors form Winston bridge. Now the triangle shaped circuit will have the equivalent form which is shown in the middle. Then modified circuit diagram will be like this after neglecting the middle resistance between the 2 points A and B. R1 is the middle resistance, R2 and R3 are the resistances which exist above R1, R4, R5 are the resistances which exist below the middle resistance R1. If R2 by R3 is equal R4 by R5, in that case potential at C and D will be same, that is VC will be equal to VD, and the modified circuit diagram will be this circuit diagram, and the middle resistance R1 can be neglected, and equivalent resistance between A and B will be R2 plus R3 into R4 by, plus R5 divided by R2 plus R3 bracket closed plus R4 plus R5 bracket closed. RAB is the equivalent resistance between the 2 points A and B. Number 12 formula or concept. In this case, again 5 resistors will be connected between the 2 points A and B. These are the 3 resistors R1, R2, R3, and fourth resistor R4 is connected across R1, R2, and the fifth resistor R5 is connected between the 2 points C, B, D and B. R4 is connected between E and C. If R4 and R5 are pulled upwards and downwards, in that case this circuit will have this type of shape. Will have this type of shape. That means these 5 resistors will form Winston bridge as shown in the figure. Then modified diagram, and we can denote the resistances between the 2 points C and D. The resistance will be R2. And what about the resistance between A and C? If we compare this diagram with the diagram existing on the left hand side, then resistances will be R4, R3, R1 and R5. According to Winston bridge principle, if R4 by R3 is equal to R1 by R5, in that case the middle resistance R2 can be neglected or ignored from this network or from this circuit. And equivalent circuit diagram will be what? The above branch R4 and R3 will be connected in series combination. In the lower branch R1 and R5 will be connected in series between the 2 points A and B. Equivalent resistance between A and B will be RAB, which will be R4 plus R3 plus R3 bracket closed into R1 plus R5 bracket closed divided by R4 plus R3 bracket closed plus R1 plus R5. This is the equivalent resistance. This is the equivalent resistance. Equivalent resistance between the 2 points A and B. RAB is the equivalent resistance between the 2 points A and B. Number 13 formula or concept will be what? Number 13, not number 14. Now 6 resistors are connected as shown in the figure. These are the 4 resistors which connected along the diagonal of a square or rectangle, and the 6th and 7th resistors are 5th and 6th resistor will be connected in that way. We have to find equivalent resistance between A and B. We can denote the resistances as R1, R2, R3, R4, R5 and R6. Now equivalent circuit diagram of the given circuit diagram will be what? R5 and R6 will be same, but R1 and R3, R5 and R6 remain same. And here R1 and R3 will be connected in parallel combination, and R2 and R4 will also be connected in parallel combination. And this is the parallel combination. These are the 2 parallel combinations. First parallel combination is a parallel combination of R1 R3, and second parallel combination is the parallel combination of R2 and R4. Now the modified circuit diagram will be what? R5 and R6 will be unchanged. R5 and R6 will be unchanged and will remain unchanged, and we can draw the equivalent resistance of the parallel combination of R1 R3 and R2 R4. Rp is the equivalent resistance of R1 R3, and Rp prime is the equivalent resistance of R2 R4. Rp is equal to R1 R3 divided by R1 plus R3. Rp prime is equal to R2 R4 divided by R2 plus R4. Modified circuit diagram will be as shown in the figure. So here R5, R6 and Rs is the equivalent resistance of Rp and Rp prime. Rs is equal to Rp plus Rp prime, that is the equivalent resistance of series combination of the two resistors Rp and Rp prime. Equivalent resistance between A and B will be what? R5, Rs and R6 are connected in parallel combination. Therefore, Rab equal to R5, Rs, R6 divided by R5, Rs plus R5, R6 plus R6, Rs. Rab is the equivalent resistance between the 2 points A and B. And Rab equal R5 Rs R6 divided by R5 Rs plus R5 R6 plus Rs R6. Therefore, Rab is the equivalent resistance. Rab is the equivalent resistance between the 2 points A and B. Between the 2 points A and B.